This video is on strategies for comparing fractions. Which would you prefer, a half a candy bar or a fourth of a candy bar? For this problem, the teacher might give the person who chose 1/2 a very small candy bar and the person who was stuck with a fourth a very large candy bar. Consider drawing pictures for this problem to see why a fourth might be bigger than a half. So the big idea here is that the size of the whole matters. So teachers need to be explicit when engaging students in fraction tasks that we're talking about the same sized whole. We can assume for the rest of this semester that we're always considering that a fraction task involves the same whole. Otherwise, there's no way to answer this question. For example, consider the likely impossible task of trying to compare a list of fractions where the size of the whole associated with each fraction could vary. Consider the following problem. Order the fractions from least to greatest, 5/8, 5/9, and 6/12, if the whole changes for each of the fractions. So the point here is that the whole unit matters. Think about how you or have you seen children compare fractions in school. So make a list of procedures or strategies you might have been encouraged to use in school, or some that you have seen as you visited current classrooms. For example, maybe you were encouraged to draw pictures to see which fraction is larger. One thing to keep in mind is this big question of, before we introduce a procedure, we must ask, am I ready for my students to stop thinking? This is an example of one of the methods to compare fractions that if you look up on YouTube, if you just do a search on YouTube for comparing fractions, you'll probably see this guy's face. Here's a screenshot from one of the videos where he compares 1/3 and 1/10. And although he does it in a very slick way, I'd like to also think that the steps that he's going through to compare these two unit fractions are probably unnecessary when he could just go back to the meaning of what is 1/3 and what is 1/10. What do those mean? And instead he uses a common denominator strategy and finds that 1/3 is 0.333, which is actually not true, and then 1/10 is 0.1, and then compares those. I'll mention later why probably shouldn't go to a strategy that has us convert to decimals yet. We don't need that strategy. It's not really appropriate, particularly when we're comparing unit fractions. Another strategy might have something to do with butterflies. I'm going to eventually discourage you from using the butterfly method. It's kind of a magic trick. It works. It has to do with cross multiplication, which is also to most students kind of a trick. If you stop and ask the question of, why are we doing this method? Why does it work? Kids and often teachers won't be able to explain that, or either won't be able to explain it or don't explain it. So going back to what happens in this gentleman's video is that he takes 7/8 and 4/5 and applies the butterfly method and ends up with some comparison of 35 and 32. Clearly 35 is greater than 32. That's a whole number comparison. I can do that. But then furthers that conclusion, and therefore, because the 35 is associated with 7/8 and the 32 is associated with 4/5, it must be that 7/8 is greater than 4/5. Here's another example of a teacher going to pretty great lengths to compare fractions. The first, number one, if you look comparing these different numbers of thirds, 2/3, 3/3, 1/3, I was happy to see that she didn't go to any greater lengths than just ordering those, because if you have the same denominator, you can just order the fractions based on the numerator. 1/3 is less than 2/3, is less than 3/3. But notice in number 2, the great lengths that she went to find the least common multiple of the denominators, and then convert each of the fractions to a fraction with a common denominator, so that she was back at the same problem she had in number 1, 5/20, 10/20, and 4/20. Whereas I think you can just back up a minute and say, wait, I know something about unit fractions. I can just look at the denominators and say, well, what do each of those denominators tell me about the fraction? So 1/4 means I'm dividing the whole into 4 equal pieces. 1/2, I'm dividing the same sized whole into 2 equal pieces. Well, each half is bigger than each of the fourths, so 1/2 is greater than 1/4. And then comparing to 1/5, well, if I'm dividing the whole into 5 equal pieces, then each of those 5 pieces, each fifth, is smaller than or less than each fourth. So we don't need this procedure that we can just go through and apply without thinking about what we're doing in order to get the correct answer of how we order these fractions. Number 3 is a little more difficult, but there's probably some extra work that's being done there when we could just apply the same idea to pretty quickly see that 3/8 is less than 3/4, and then 2/3 and 3/4. That one's a little harder, but there might need to be some procedure, although eventually in this video you'll see where we can just think through the process of comparing 2/3 and 3/4. So another technique is to draw pictures. Consider how you would draw pictures to compare 2/5 and 3/8, and then also note that these two fractions are 1/40th apart. So your pictures might look something like this, where you've got two representations, two rectangular representations, one for 2/5 and one for 3/8. Notice that the whole here is the same for both of the fractions, but even a very careful drawing is not likely to settle the issue of which one is greater. It looks to me from this picture that they're about the same size, 2/5 and 3/8. In fact, they are pretty much the same size. They're only 1/40th apart. I would not rely on this strategy because any inaccuracies can throw things off, and you can see from the picture every student drawing is going to be inaccurate to some degree. My drawings certainly are. Another possibility is getting a common denominator. Consider getting a common denominator when you compare 96/98 and 97/99. I don't really want to use this strategy for these fractions. I would advise not relying solely on the common denominator strategy as your comparison strategy. What about changing the fraction to a decimal? And also note that decimals come in the curriculum after fractions, especially after we're trying to compare these fractions. So try comparing these same fractions, 96/98 and 97/99, with a paper and pencil algorithm or with a calculator. Is that a meaningful process, or is there maybe a more straightforward way? So when fraction comparisons are first expected in the curriculum, converting to a decimal is not particularly helpful. And then again, this cross multiplication or butterfly method, try it with 2/5 and 3/8 and say, is that meaningful? Probably not. You'll end up with maybe comparing 16 and 8 and 15. Still, I would always want the child to be able to answer the question of why are you doing this? What is going on? Why is it that you're multiplying 2 times 8 or 3 times 5? What do those numbers mean? There are answers to those questions, but we often don't get to those answers or don't require the child to be able to answer that. So we strongly discourage using this generally non-conceptual approach, especially when there is a much simpler conceptual approach. These are tricks to get answers, and we don't think these are very helpful. So just a little bit about the research here. American students have a fairly weak understanding of fractions in general. In 2004, the National Assessment of Educational Progress, 50% of the 8th graders could not order 3 fractions from least to greatest. It's disappointing. It's not particularly surprising. But in 8th grade, students are expected to have mastered division with fractions, let alone comparing fractions. A little more from the research. Teaching fractions often focuses more on memorizing procedures than understanding. This teaching practice is linked to negative outcomes, as students have difficulty in remembering processes that they learn without understanding. Moreover, when students have not yet developed conceptual understanding, they usually invent the processes they have forgotten and generate their own, often incorrect, algorithms.